Okay, we should start. So I'm just giving you a warning that this presentation of this lecture has a lot of new materials, and I was getting really excited to sort of redo all the course notes accordingly. And then last week, all sort of administrative stuff broke down. Then they published a paper on 40,000-year-old writings, and then I had to give a couple of interviews with journalists, not my paper, but I had to give comments. And so I haven't updated the course materials, which means that I haven't written down all the explanations for the new stuff that I'm presenting today. So if it's unclear, even more than usual, raise your hand and ask a question. So the first thing is, do you have lingering questions? Everything is clear. Okay, hard to do it blank. So I've gone through most of the assignments that you sent. I should have sent you group by group feedback. And generally, it's actually quite good. So well done, everybody. And please make sure that you submit a separate pre-needed report, because that was a general problem. There's a few groups who didn't, and then I didn't manage to get to give feedback on that. There's one thing that came up both in class and in reading your assignments, that sometimes we want to use algebra to do smart things with our formulas. So for instance, right, we've seen last time that if we want to calculate the Wednesday-Lewis shift, we need to create new variables, right? For instance, whether we're in a win situation and whether we are in a lose situation, so that the parameters that are defining, let's say, whether we should stay with the current choice only apply when we're winning, while the parameter that says whether we should shift choice only applies when we're losing. Right? And so I thought I would spend a few minutes just trying to walk you through some algebra that we can use to tell the model these things without having to do a lot of if-else checks. And so if you remember, right, we have Wednesday, which might have a certain probability, and we have lose shift, which might have a separate probability, right? And so a probability of staying when we win and a probability of shifting when we lose. And so given that we're moving in a space where we're not coding staying as 1 and shifting as 0, for instance, but we're coding right as 1 and left as 0, we need to convert the previous choice in a space where we can move, right? So if we increase the probability of playing right, we're going in the positive direction. If we're decreasing the probability of playing right, we're going in a negative direction, which means that what we can do is we can convert the previous choice to a positive or negative number. So if we want to go from a 0 to 1 scale to a -1 to +1 scale, right? We can think it through, play with it in R, but basically we can use 2 times the value of the choice, which is a 0 or a 1, and then it's -1, right? I didn't put the parentheses there because, as you very well know from your, I guess, primary school days, we first apply multiplications and then we apply minus and addition and subtraction. So these, if you have a 0, 2 times 0 is a 0, minus 1 it's a 1, and minus 1. If you have a 1, 2 times 1 is 2, minus 1 is 1. Then the second thing that we need to do is that we need to switch the component of, this component of, when we lose, right? We want that to be multiplied by 0 when we're losing, without explicitly telling the program if we lost. Does that make sense? So we just make an equation that automatically switches off component according to the values of the variables. So what we can do is we can use a variable we already have. We have a very convenient variable, which is called feedback, which the way we coded it so far is 1 if we win and 0 if we lose. Right? So if we say the feedback times 2 times c minus 1, this variable is completely switched off every time that we lose. Does that make sense? So it can be minus 1 if we won and we were playing left, right? So we want to stay with a low probability of picking right. It's 1 if we won and we played right. So we want to stay with a high probability of playing right. It's 0 in all the other cases. If we want the other component, right? Again, what we're going to do is we're going to do these very basic algebra. We're going to say 1 minus feedback, 2 times choice, minus 1. Here. Because this switches the feedback to 0 when we won and to 1 when we lost. Do these things have to come naturally to you? No. I'm just showing you that we can use very, very basic algebra to sort of simplify our life, right? Not have these nested if and else. With the kind of models that we're using now, it's not a problem. Everything is going to run very fast. As you might want to go into a much more complex model, not having an if-else check actually can make your model substantially faster. Or especially if you don't have many if-else checks all the time. Does that make sense? Another small computation trick is, of course, if we put this in the likelihood in the model chunk, these things are going to be recalculated at every new sample of the posterior space, which again, is very fast in these models, but could be a drag. So what we can do is we can take a chunk that's called transform data, which we will talk about later, and actually pre-calculate these values for all the trials before we even go to the model. But still, no if-else means that we can calculate them for every row very quickly. Yes?
I just have a question to the separate printed report.
Separate?
Another paper.
Yes.
What is it? What?
Oh, it's because some people only submitted a markdown. And then when I look at the markdown, I cannot really see the pictures unless I go and check them in the repository. For instance. Or some people just sent me the full notebook with all the code and all the text. And that made it much harder for me to sort of be able to quickly see what was going on and only check the code for specific things. Good. Since I know you now all love algebra, I made another one, which is another example of this. So some of you last time were discussing a model called the sore loser, right? I don't know why I wrote loser, but so it's a model that plays the reinforcement learning, then loses 3 trials in a row, and it becomes the bias agent. And then as it plays, if it wins 3 in a row again, then it becomes a reinforcement learning agent again. So we could fit this model with a very complex mixture model, or we can try to do the same trick. Right? We can create a variable which is 0 when the agent hasn't lost 3 trials in a row or has won 3. And the not loser, which is 1 minus that. Then we use these to multiply the bias agent formula, which is basically a theta, right? Plus the not loser times the reinforcement learning agent. And that gives us this mixture of models as one equation, one likelihood, and makes our life much easier. Does that make sense? Yes.
I think it makes sense, but is it then like what you call a mixture model? Is the last one a mixture sense?
It is.
Yeah. Okay.
Except we're not saying that for every trial there is a certain probability that it's using model 1 and a certain probability that it's using model 2. We're actually saying that for any given trial, we know in this case which model we're applying. But still, we can estimate both the bias and the learning rate and the inverse temperature tau within one likelihood. Yes.
It's also where you don't want like else.
Yes, exactly. This also it's both more elegant and it saves some computation. That said, this is a fantastic segue. Since I've been too busy this week, I haven't tried this. And so sometimes what happens is that I do some very clever algebra, and then Stan tells me, actually, what you've done is breaking the continuity of the posterior space. So a bunch of divergences. And then I have to go back to the evals. But I still enjoy doing this a lot.
Does it explicitly tell you that's the problem? You just get the divergences.
You get a lot of divergences, yeah.
And then you know it's problem.
And since I've been trying to be clever,
yeah.
And usually I would never recommend to say, start with this.
Yeah.
You start, let's say, with this, and then it works. And then you fit this, and then it works. And then you put them together, and then you get all the divergences. Okay. And that's kind of a good way of knowing where the problem arose. Never start with the model you actually want. Start building things step by steps. And indeed, that's what we're doing in this early part of the course. We're starting with models that are not really good models of things, right? And then we build up. Yes?
Why would this occur with if-else statements?
Because the if-else, so here, it's basically if you change a bit, how was it? If you change a bit the posterior value, then what happens is that it might, well, this is not the trial by trial run. Actually, I need to think about that, but it happens, yes. And when I discuss these things on the Stan forums, then it's the discontinuity that this tends to introduce discontinuity in the posterior space. But I need to think about exactly how it works.
Intuition, because I think that introducing a first state would also introduce discontinuity.
Well, so it's not sampling the posterior space unless the conditions are met. While here, suddenly the value of theta here is still sampled in the posterior space, even if then it's multiplied by 0. And the log posterior probability is expecting that with a small change of theta, you're going to get a continuous change in the likelihood. But actually, these is the only things that are affecting the likelihood, the parameters of the reinforcement learning. And these are not. And that creates kind of a problem for the sampler. Right? That's the best explanation I can improvise on my feet. But does that make sense? Yeah. So you're changing these values, and you're thinking that they should all change the likelihood. You're assuming that they should all change the log posterior likelihood. But only some are. So changes that you would expect to change things are not changing. And that affects the physics of the simulation, right? So suddenly one dimension is not mattering for your calculations anymore. But you were expecting it to matter. Okay. So where are we? We theorized models, we formalized and simulated generative models, starting from the model, creating data. And now we're building inferential models that can make inferences on data. That is, we're going back from the data to model parameter values. So we wrote a first-hand model that has at 3 chunks, right? Data, where we put whatever input the model requires. Parameters, which are the unobserved variables that we're interested in. In reinforcement learning, that would be learning rate and tau. And model, which is the chunk where we're connecting the parameters with the data. We're telling Stan what's the mathematical shape that this relation takes so that it can calculate plausible values of the parameters given the data. Now we're going to dig a bit deeper into that. We're going to look at how we fit these models, and then we're going to work on what we call the Bayesian workflow. That is how we assess whether these models are making any sense. So this is the model so far. It's not very easy to see, but that's where we ended up last time. We have a data block with the number of trials, with the vector of choices that the agent is doing. And this is stuff that we're feeding to the model. We are trying to specify the nature and boundaries of the variables as much as possible, right? Integer lower 1 for n, because if our experiment has fewer than 1 trials, then there's a problem, right? If it has 1.5 trials, then there's a problem. The choices are integers with a lower value of 0 and an upper value of 1. There can only be 0 and 1. Would the model work without those boundaries? Yes. Why do we put them? Because let's say that we have several data sets, one in which the choices are coded as -1 and 1. These is going to give us an error and let us see the problem. To the parameter block, we're still building the simplest possible model, the bias agent. So we have only one parameter, theta, the rate, the propensity at which the agent picks right. It is a real number because all decimals between 0 and 1 are valid. And it has boundaries at 0 and 1 because it's a probability. Then we have the model block where we define the priors and the likelihood, right? We've seen last time that we can put a prior on theta, which is already on that scale. What's the distribution that's already on the 0 to 1 scale? That's the beta distribution. You've had Josh and Andreas last semester, so you're friends with the beta distributions. We put alpha of 1 and beta of 1 because basically it's a flat distribution. And then we have the likelihood, which is saying that the choices of the agents are generated according to a Bernoulli function, which is a function that spits out 0 and 1s according to a rate. And we say that indeed, H is a function of theta, right? And the model will use these to say, given the possible values of theta that I'm sampling in the posterior space, how likely are they given the data we actually observe? Yes?
Are the restrictions, the lower and upper restriction on theta necessary if you assume a beta distribution?
Yes, but we want to be explicit, right? We want to state everything we know so that this code becomes easier. And keep that question in mind because something is going to happen in the next couple of slides. Yes. So are there questions on this part? Right. Again, I'm not expecting you to be able to write them, blindfolded, but just the general structure and what to look at.
I seen some standard, but never using the target
Mm-hmm.
or whatever is variable in the model block. I've only seen it as like, say you give it some
Tilde, normal, parenthesis, yes.
Yeah.
So that was the old way of specifying things. That would have been H distributed as, this would be Bernoulli, and that would be a theta, right?
Yeah.
So these is gonna, I can't remember if it's already being, what is called discouraged. There's a specific term, now I can't remember it. Deprecated, but it will be. Because the idea is that what we want you to focus on, also very pedagogically, is that at each step in the posterior space, in order to calculate the log posterior probability, you need to sum up different components.
Yeah.
In this very simple case, we have the likelihood of I always said mixed likelihood and probability. The likelihood of the theta values given the choices, and the probability of the theta values given the prior.
Yeah.
And you need to sum it up. That's the posterior. Otherwise, it would just be the likelihood and not the log posterior likelihood. As we get to more complex models, we might have 6, 7, 8, 20 components that need to sum up. And these tells us exactly which components are being summed up. So it's less intuitive to start with, but it's a good tool to know what's going on in a complex model. Yes. I think that at this stage, even if they already have been deprecated, which I don't remember, you can still write things in the other way. Yes. Good. Oh, done that. More questions? Okay. So this used to be, I think now we've settled it a bit more, but it used to be kind of a fun conflict between me and Josh, right? Whenever you have a rate or something, Josh would always recommend a beta as a prior. And coming from teaching method 3 and method 4, right, I always argue that it would feel very counterintuitive to you. Because when we have a model that is using a rate, which kind of, how do we deal with that? So to be even more explicit, you've met a bunch of cases that have as an outcome a 0 or 1, logistic regressions. Right? And how do we deal with the 0 and 1 boundaries when we build a logistic regression? Yes?
The logit.
Exactly. So we use the logit function. Right? And if you've done logistic regressions in methods 4, right, that is recommended because in a logistic regression or in any kind of models, you have a bunch of different components, right? A bunch of different predictors with a bunch of different betas. And it's kind of difficult to constrain them all together so that they will only sum up to 1 or 0. once we do a logit transformation, we are moving in a minus infinite to plus infinite space. We can put as complex models with as many parameters as we want inside that. And then it sort of get automatically shrunk at the very end into a 0, 1 space. And there are interesting ways of doing that with the beta, but I find this one more intuitive. So what we can do then is to say, what if we use a logit transformation? And then which kind of priors would you put on the theta? This is the beta 1.1, yes.
You could do a Gaussian.
Yes?
Yeah.
What would you?
I guess do like, I don't know, maybe standard deviation of 1, 2. That looks good.
Yeah, so here is a 0. That's why you visualize things all the time, right? So here is a 0 with a standard deviation of 1.5, which is very comparable to the beta, except that we don't really believe it's going to have exactly 0 or exactly 1, which to me makes better sense, right? If you had gone for a 1, it would have been a bit thinner. If you had gone for a 2, I think it would have started going up here. Why would it go up at the boundaries?
More density toward the edge, right?
Yes, so here is the 0 to 1. Here is the sigmoid. Right? So if we start, and this is minus infinite and plus infinite. If we start putting a lot of mass here, even if it's hard to move towards the boundary because of the nonlinear transformation, enough long tails will sort of sum up to an increased probability of exactly or almost exactly 0 and 1. So that's where you play with visualization until you find something that you're satisfied with. And this is what we call prior predictive checks, and we'll talk about that later today. So if we wanted to use that other parameterization with log odds and normal priors, this is how it would look like. In target, here for the prior, we have a normal log probability density function with a mean of 0 and a standard deviation of 1.5. And here, we can actually use a neat trick that Stan has implemented, which is called a Bernoulli logit LPMF instead of a Bernoulli LPMF, which the thing that it does is it takes log odds as a rate. We could do the transformation, blah, blah, blah. Stan has given us a tool, why not using it? We just need to understand how it works. Yes. So how does this make sense to you? Right? Do you notice anything wrong? And I know it's hard to see. Yes?
So the boundaries of theta don't make sense.
Exactly. Right. So this is where my assumption from before then suddenly makes me realize that I haven't reconceptualized what the theta is. And so the model would spit out a lot of issues, right? I'm trying to sample and the sample got rejected. Meh, I can't do stuff, right? And then you need to go and figure out why things are being rejected. And so in this case, it could be seen as counterproductive, having specified those things, but also it reminds us, look, now the theta is log odds, and we're going to have a hard time conceptualizing them. So what we can do is we can learn to love another chunk in Stan, which is called generated quantities, which is a chunk that allows us, once the model has been fit, to perform super fast calculations for variables that we might be interested in. In this specific case, theta now is an unholy mass of log odds. We want to go back to our probability space, which we understand better, the probability of picking right. And so inside generated quantities, we can create a new variable called theta p, theta probability, right? Which is real, bounded at 0 and 1. And then we can generate it by saying that theta p is equal to the inverse logit of theta. Right. Generated quantities is going to be a workhorse in the Bayesian workflow because we're going to need to generate a lot of diagnostic checks. And that's the best and fastest place to do that. We could do it in R. We could fit the model, extract whatever the parameters are already there, and calculate these things in R. So InvLogit is not going to be too computationally heavy. But these is going to be compiled into C++, which means that it's going to be super fast, right? So again, as we move into more and more complex models, having good practices and doing things in the right place can save us a lot of headache. And at this stage, it's conceptually quite easy to see what we're doing. Yes, so this is again a message from students from the past. Remember, only do the inverse logic at the very, very end when everything else has been run, because in previous years, people got lost in trying to, each separate component was inverse logited, and then the results didn't make sense. And also maybe call the parameters not theta and theta p, but theta logit and theta p. So you're actually very, very explicit about what is going on. Oops. Did you have a question, Christian?
Yeah, it was more like hearing stuff just for myself, but I think for me, I can just ask, but is it correctly understood that the model is still working in this infinite space in a way? So it's almost like a visualization thing, or it's like about in the end, we can express the posterior as if it was the representative space.
Yes.
But it is actually still sampled in the infinite space.
Yes. So Stan is a free horse. It's a free spirit. It doesn't want boundaries. The parameter should be unbounded as much as possible. That's going to save you a lot of headaches. But while for Stan, the unbounded spaces are very useful, for our limited minds, they are not. So in generated quantities, then we take and we retransform things as we understand them better, as we can visualize them, et cetera, et cetera. And that's for us, right? The model is not changes. It's just post-processing processes. Yes. Good. We have the model, right? It's a nice model you have there. It'd be a shame if somebody were to fit it to data. So if you have models like you're very satisfied, it's not giving you syntax errors, but the data are very often going to break it, right? So the best laid plans always fail at the first meeting with the enemy. So how do we feed it to the data? Well, first we need to prepare the data so that they're in a format that Stan can understand. So we've seen in Stan, right, that we're saying, oh, there's a number, which is n, and then there's an array. And this is a different structure from what we used to when we talk about tables and data frames, right? Tabular data. So how do we create that? Right, we can say if D1 is the data we save from a simulation in which the random bias agent at a rate of 0.8, whatever, we can say that data that we're going to feed to Stan is a list in which n is equal 120 and h is equal to the full column D1 choice. Have you worked with lists before? I guess if you've done Python, you do that regularly, right? Do you feel uncertain about lists? Well, the basic idea is that they allow us to put together things that can be very different. We could put a matrix, we could put a vector, we could put a string, we could put all sorts of things there. And they're often convenient, as for instance, in a table or in a data frame, we would need to repeat 120 times, right? If we want to add a variable, we can't just add one value. We need to add one column so that for every rows, we have a specific value of that variable, right? Which when we work with big data sets can become cumbersome. It's not really the best excuse in the sense that if you're working with big data sets, you might want to work with SQL instead of these things. But it conceptually analogous to what's happening in Stan. Right? And so we want to use the lists to sort of match that logic. So all the elements that you're defining in data have to be parts of a list and have to have the same name as they have in Stan. Right? On that, yes. Okay, so then what we do is we can take our Stan file. Now, I haven't told you how you save a Stan file if you write it in R or how you call it in, but there's the course note for that because that conceptually is very trivial. I just want to say you now have what is called a location for your Stan file that you saved. That location is within Stan file Bernoulli. And now we can tell to common Stan that our model is in that specific place. I'm also adding there 2 arguments to confuse you and instill fear. No, it's because I like when you go and look at stuff on the net, you always get a lot of arguments, and I want you to have a certain familiarity with these things. So the first one is telling where the model is. The second one, CPP option list Stan threads equal false, is saying we haven't optimized these model so that a single posterior sampling should be parallelized. If we wrote true, then the model, the common Stan, would expect that we've done stuff to the Stan code that allows to the sampler, when it's looking around to figure out what the gradient is, to split that processing to different processors, right? We'll see it later in the course. I don't want to confuse you too much now, but there is an argument when we're compiling the model that tells the compiler whether this is made to be parallelized or not. If you don't write anything, it takes false for granted. Right? The second is called stanc option list 01. So in the way that the sampler works, there's a bunch of hidden parameters that the Stan developers are always playing with. And you'll see that sometimes the cutting edge people on the Stan forum, or when you ask people on Blue Sky or wherever, or maybe, I don't know, Gemini or Claude is telling you to add, oh, list 03. That's one of the hidden settings that people are experimenting with. The default is pretty good. Right. So I think that now the default is 01 and it works very nicely, but you often see that people add that because they are trying different settings of how it's optimizing the hyperparameter, how it's optimizing the step length and the number of steps. That will run for, I don't know, 30 seconds, depending on your computer, 10 seconds to 1 minute, and it's converting the Stan code to C++, which is then compiled to machine language, right? So it runs very fast. Then once we have these mod Bernoulli, this is an object. So we can actually call methods on that. What is a method? A method is the equivalent of running a function on that object, but the function has already been defined inside the object, right? So usually you have a data frame, right, or whatever, that has no function in itself. It's just a sequence of numbers organized in different ways. And you write a function that does thing to that. For instance, standardizes all the values in the second column. When we talk about objects, the objects can combine both data and methods or functions inside the object so that you don't need to recode it. It's already defined there. So here, these objects that the model Bernoulli has a method that's called sample from the model. Sample. It takes some data, the data we created before. It can take a seed if you want to make it reproducible. It takes a number of chains, that is how many times you want to have the sampler go. So we can compare whether the results are the same. Here I put 4. Should these chains be running one after the other sequentially? Or do you have processors to spare so that you can set them running at the same time? Given that you all have computers that are decent. So here I said I want 4 chains. I want to try the process 4 times and see if I get the same result. And they should all run parallel. It's not the same thing as before. We're not splitting processes inside the sampler. We're basically running 4 times the samplers. So we don't need to change the code in the stand model. How many iterations should the sampler have while it's changing its step size and its number of steps? I'm giving it 1,000. Why it's 1,000? Because it tends to work. There's no deep theory in that. After it has done how many times it has to sample, here I'm giving it 2,000. I could give it 20,000 with the kinds of models we have right now. It doesn't matter, but 2,000 should give us 8,000 posterior samples. 8,000 samples should be decent enough to run, to draw a very detailed posterior distribution. And I want it to update, to give me a message every time that 500 are done. If your model is complex and you don't know how it's working, you might want to put it lower, right? So that you know, because sometimes I stare at the screen, go get a coffee, get back at the screen, and it's still exactly at the same point. And then I realize, oh, this is a very complex model, and I put refresh every 500. I don't know whether it got stuck or whether it's still running. So I put it at 10 with complex models, right? So you actually can see whether it's progressing. We've discussed a bit max tree depth and adapt delta last time, right? So max tree depth is how far in the future can it look to see whether it's going to do a U-turn and end up in the same place, which would be a very inefficient way of sampling the posterior space. And adapt delta is how much it should learn, how much it should adapt its step size and its number of steps as it's trying out things at the beginning. The default is 10 and 0.8. They're pretty fast. They work in normal cases. I usually put them already at 20 and 0.9 or 9.5 because with simple model or with trying out things, I don't care if it takes a longer time at the beginning because I want to know that the errors that are being spit up is not due to suboptimal sampling, but to me fucking up the code, right? And the concept of the model. Does this make sense? So this is a good place to take a break. Okay, we should start. Okay, We fit the model. Now we can simply call it. We can say the name of the model and then $sign the method summary. What we get is a table. So we're back on familiar grounds. We have name of the variable, mean, median, standard deviation, mean absolute deviation, 5th quantile, 95th quantile, R hat, ESS bulk, ESS tail, lots of stuff that we don't know what it is. Right? But let's focus to start with on the stuff we know what it is, right? Variable, mean, and then we could look at different measures of variance, but let's look at the standard deviation, right? So we are getting something called LP. It's the log posterior. We're gonna go into the details of that when we're gonna do model comparison. So I allow myself to skip it for now. Then we have the theta parameter, which tells us that it goes as a mean of 0.8, standard deviation of 0.3035, and it roughly goes from 0.742 to 0.858, right? So it seems pretty spot on, given that we had given data from a bias agent that had a theta of 0.8. Then we look at prior theta. I can't remember if I put it on the slide, but we can add to generated quantities, like a way of saving also the prior. And I'll cover it in a couple of slides. Here we get that the prior of our theta, which if you remember, I think in this case, it was just a beta still. So a beta of 1 and 1, so completely flat distribution, has a mean of 0.5, and it goes roughly between 0.05 to 0.95. Does that make sense? Is it good? Estimates of the prior? It's not a trick question. Why is it not?
Because sometimes you want to do broad range where even.
But what is our prior? Is it broad ranged?
Oh yeah, then it's actually it's 0 and 1.
Yes.
Fitting with your quantile.
And really it's saying the 5th quantile is 5%. The 95th quantile is 95%. Actually, it seems it's, yeah, right? It makes sense. Then we do the Bernoulli logit model just to see how the output changes. What we have is the LP. Let's ignore it. The theta logit, and it's 1.430. Oh, no, it's log odds. I don't want to look at that, right? We look at the prior theta. Again, it goes from it has a mean of approximately 0.5. And the quartiles, they go from 0.08 till 0.92. So they're a bit more restricted, which makes sense if you remember our plots. That was discouraging 0 and 1. Still pretty broad, right? And then we have the theta that we generated by doing the inverse logit on theta logit. And you can see that I haven't updated these outputs, so I need to do that because it should be theta p. So it's the estimated 0.8, and here it goes from 0.74 to 0.86, right? Which is really indistinguishable from above, right? We're getting exactly the same kind of inference. Does that make sense? Which is also right, when you're playing with different parameterizations of your model, it's nice to try out these things so that you can actually compare whether you're not messing up things. Yes?
Why are we interested in the prior?
Yes.
You defined it, so we already know what.
Well, first of all, it's a sanity check. Sanity checks are always good.
Okay.
And then in a second, or in a few slides, we'll go into the need to check for what the model thinks when it hasn't seen the data yet.
Okay.
Here we have one prior. It's easy. Let's imagine reinforcement learning, where you have a prior for alpha, the learning rate, and a prior for tau. How would these prior determine the distribution of 0 and 1 choices? That's going to be tough, right? So we save the priors, we run predictions using the priors as parameter values, and then we get a distribution of outcomes. Yes?
So is doing like a built-in prior predictive chain? In a sense.
We are going to build it in ourselves. Yeah. Okay. Then we plot. That's also another reason for putting in there, because it generates those variables so we can use them for plotting. Here we look in red at the prior for the beta and for the logit model. You can see, again, it's very hard to see, but it's slightly narrower in the logit. In blue, we plot the posterior, and in black, we put the actual value from the simulation. And in both cases, they're doing pretty good, right? We can see, actually, no, I think it's all within the unsurvey. I'm not gonna speculate about small differences there. Yes. So before we move on to doing all those predictive checks and stuff and Bayesian workflow, I also wanted to introduce you to another recent development of Stan, which is called Pathfinder, which is a way of very quickly running your model without doing the full Markov chain Monte Carlo, so you can test things quickly. For instance, what's the impact of priors on your expectations? And so, I don't know, have you been introduced to variational Bayesian inference in the whole free energy, blah, blah, blah thing?
Briefly mentioned, I think.
Okay.
Perception.
But okay. Yeah. Not this is just because I need to know how much to specify in terms of differences from what you already know. So this is a variational method. We'll know what variational is in a second, which is used to do approximate Bayesian inference. So it doesn't sample the full posterior space as MCMC, but it's using tricks to navigate it very quickly, and that makes assumptions. It's a complement to MCMC for different reasons. But first, let's look at how it works. Instead of fully sampling the posterior, it basically does gradient descent. So you parachute an agent in the landscape. It looks at where it's going down, and then it goes in that direction in big steps until it finds a minimum. And then it starts doing small steps and identifies the exact minimum. Then it stops there. It uses now these minimum as the mode of the posterior distribution, and it uses its path to assess the variance of the posterior distribution. It's not exploring all around it, but it arrived here in this way, and it was pretty steep. So it's going to assume that the standard deviation is going to be very small. The variance of the posterior is going to be very small. And then it says, it's a Gaussian. And this is the standard deviation, and this is the mean. Since this is very fast, and we don't want to get trapped in the first local minimum, what we can do is we can take 1,000 agents, parachute them at different places in the landscape. They all do their very fast operation, and then we take the lowest minimum. Right? This runs orders of magnitude faster than MCMC. So I was running a hidden Markov model, which we might end up talking about later in the course, which would take about 10 hours to run on my computer. And with the Pathfinder, it took about 6-7 minutes. It's an approximation because instead of sampling the full posterior distribution, it assumes a multi-normal Gaussian because all the components of all the parameters that it's trying to estimate are considered to be Gaussians. They're correlated to each other. And it then gives us the standard deviation and the mean of each of those. Then if we want to do visualization, as we've just done, it simply takes those parameters, the means and standard deviation, it generates data from that, and it gives us the posterior. The use cases are, you can use it to very quickly prototype. So you're trying out different variations of your model. You just want a very rough idea of which kind of expectations it has, or whether it's completely failing on the data, and so on and so forth. You can use this not to have to wait the whole time. What I mostly use it for, though, is the Hamiltonian Monte Carlo, the Markov chain Monte Carlo that we usually run. They start at random. They might start in a very crappy region of the posterior, right? Which is very sparse, and therefore they learn to make very big steps. And then they need to relearn and change over time, and that takes time, right? Or they're not adjusted for other regions of the space, and you get divergences. But Pathfinder might actually find okay regions from which to start. So you can run a Pathfinder bit of your model and then pass its posterior estimates and tell MCMC, start from here. This is where you initialize your agents, right? Which in some of the, so for instance, in the hidden Markov model, it made it run in like, I can't remember, 8 hours, which was 2 hours less. There's a paper there if you're interested, but here is the way you fit it. So instead of using sample, you use Pathfinder as a method. You give it the data, the seed, the rows, the number of paths, and the paths are kind of like the chains before, and then the single path rows. So how many times it has to sample before it's okay with having found the minimum. And then we run the model. We look at the posterior. In red, you can see the MCMC, and in blue, you can see the Pathfinder. Is slightly overconfident, but it's really the same kind of estimates for this model. Right. Then I want to just show you how you feed the how is it called, the posterior values, posterior estimates of Pathfinder as initial values for MCMC. And so again, we have our model, we use the method sample, everything is the same, but then we specify that in it should be the model up there that we just fit with Pathfinder. And then since I'm trying to keep myself honest, I ran, are the posteriors the same? They look exactly the same. Perhaps the Pathfinder plus MCMC is slightly more confident, but I don't think there's anything reliable there. And then I look at the time that it takes to sample. We can see that the standard MCMC, it's about 0.3, so it's 365 milliseconds. The Pathfinder is 158 milliseconds. And the Pathfinder plus the MCMC in this case is actually taking 492 milliseconds. It's terrible. But it hasn't really given us much. But again, I wasn't really expecting much in these simple models. I'm just giving you kind of the cutting edge tools that are being developed. Yes?
So in more complex methods, the reason you use Pathfinder only to sort of give a better initial starting value for the MCMC, is that because you don't trust serial distributions to produce as much as you do the Monte Carlo?
Exactly, because the Monte Carlo is extensively exploring the space. So it might even end up saying, oh, the learning rate, posterior probability is like this. Or it's really picking a here, but there is a long tail here. While the Pathfinder will always assume a Gaussian. Variational inference that Peter Wohler was introducing to some of you is like Pathfinder, just a bit dumber, because it's not using its path to estimate the variance. It's just looking around itself and then giving you a standard deviation based on that. Also, it could be that Pathfinder, if you're unlucky, right, it ends up being all focused here because it's kind of a good spot anyway Yeah. So you never know whether it's good enough. But it's very good to test whether your model is working and to find some initial values. Or, if your model is too complex, then you might try with Pathfinder. You shouldn't trust it too much, but it can give you some ideas of where the probable region is and check whether there are specific issues there with the MCMC and so on and so forth. Yes?
My intuition about feeding initial values to MCMC would be that if the posterior is, I'm not sure, like complicated, could we end up with it not exploring? Probably. Or are we somehow guaranteed that it will do that even if we feed it?
So MCMC is guaranteed, no matter the initial values, to find the true posterior distribution given an infinite amount of steps.
Okay.
Iterations, sorry, not steps. But we're not running an infinite amount of steps. So yes, there is a certain risk. The good thing about Hamiltonian Monte Carlo is that it has this momentum thing, which tends to get it out there. Yeah.
And I guess we already know the diagnostics more or less.
The
way to diagnose a sample is
yeah. So I think nothing is ever 100% risk-free, but this, it's not really changing the internal dynamics, and it's just giving it a slightly better start.
We're not getting new problems, I think that's what.
Yeah, exactly. Especially now, so up to a few months ago, you had to extract the parameter values from Pathfinder and then figure out the right structure to feed them to the MCMC. Now they made this very neat thing that you can just feed the model and it automatically finds out. Yes. Good. So Bayesian workflow. It's about ensuring we know what we're doing. I'm just going to move these away. And so there's model diagnostic, which are telling us, can the model properly explore the posterior space, right? We're going to see free depth, divergences, EBM, FI, R hat, and ESS. We'll discuss them. Some now, some as we get problems with more complex models. But, it might explore properly the posterior space, but still we have given it crazy expectations, right? So we always need to do checks of what our priors are doing to the model. So as we move to more complex models, what does a prior on learning rate that is centered at 0.8 and has a standard deviation of 1, and so together with a prior for tau, which is centered at 1, it has a very long tail, mean for our expected behavior of the model. Right? It's hard to conceive it in advance. So what we want to do is we want to run the model on the priors only and generate predictions. This is what we call the prior predictive checks. We want to know which expectations are we imbuing the model with. We also, once the model is run, want to do the same from the posterior estimates. In other words, once we train the model, is it able to match our data? This is not a trivial question, as you might think, because think of somebody fitting a Gaussian distribution to response latency time, reaction time, right? So this is going to be the prediction of the model, but maybe what the data is actually something like this. This is the best that the model can do, given we told it had a likelihood function that's Gaussian, but it's not really fitting the training data that well. We also want to see not only whether it's fitting the data well, but whether the model has learned from the data. Right? This is what I call the prior posterior update checks, where we simply plot, as we've seen before, right, the prior and the posterior, and we see how much our expectations, evidence has moved from the one to the other. There are formal tests for that. I tend to like the qualitative inspection of the plots. We need to do parameter recovery and or simulation-based calibration, which is now we can see that on this one simulation, things are working well, but would it work well across a plausible range of values? So if we have reinforcement learning rate that goes from 0 to 1 in steps of 0.1, fully cross-gridded with values of tau that go from 0.5 to 10 in steps of 0.5, right? Is the model going to be able to discriminate from the data these possible values all over the place, or is it going to have issues? Yes?
So when you do that, do you fit a complete model to a complete set of similarities?
Yes.
But that takes a long, long time.
That's where we're going to introduce simulation-based calibration, which is a way of both taking uncertainty into account better, and we'll see that, but also to speed up the simulations or the process. But yes, in general, it takes quite some time. And then we're going to look at sensitivity analysis. Right? So how robust are our findings to the specific choices that we made? So a very intuitive example is if we made our priors a bit more uncertain or a bit more certain, how would our results change? If we had collected 10% fewer data points, how would our results change? So how robust are they in what we are? How dependent are they on the specific choices that we made? And again, we're going to use a package called Prior Sense, which is some of the new stuff that I added, because it does it in a smart way. So we don't need to rerun things a million times. We'll also see more stuff later on, let's say out of sample accuracy. So if we take some of the data out, how well it's able to predict it. Model recovery, if we have two models generating the data, can we actually reconstruct which model is generating which data sets, blah, blah, blah. So this is not a comprehensive Bayesian workflow, but it's our starting point. Good. So the first thing is some sort of model diagnostics. So what we can do is if we fit the model, I put here 2 because it was easier to visualize with 2 chains. We can plot the value of theta that it has sampled at every iteration. And then it gives us this shape, which if everything went well is called a hairy caterpillar. Right? We can look at whether a single chain has got stuck somewhere. Sometimes we'll see that it gets stuck and then it moves up again. And we can see whether both chains have covered roughly the same area. So sometimes some of these iterations will be missing because what happened is that we broke the physics of the particle. The particle, if you remember, was given its kinetic energy, so how fast it had been moving before, and the gradient around itself. It's going to calculate how the trade-off between kinetic and potential energy is going to change at the next step. If then it does the step, if the values don't match, it says I've broken the physics, right? The gradient changed too quickly for me to be able to anticipate it, or I bump against a wall, right? And therefore we have what is called divergence, or we have low energy something, EBFMI, according to in how many dimensions the trade-off got broken. This means that there are portions of the posterior space that the model is not able to effectively sample. Its steps are too big, right, to sample that quick change in gradient. So we should do something to the model. Stan is very vocal and it says divergences. If you do errors, models that are even moderately incorrect, you can get all iterations being divergences, which is a feature and not a bug, because the model breaks fast and breaks easily. Right? So you can fix it. We could also see that, let's say, one model was exploring a mode in the posterior space, one chain, and the other was exploring a different mode, and they got stuck there. The two areas might not be overlapping. We get a statistics or an index out of that that's called the R hat, which is if it's 1, they're perfectly overlapping. If it's above 1, it means that they're not perfectly overlapping. Anything above 1.1 is a cause of serious concern. We also want to know, as these sampler is moving in the posterior space, how hairy is the caterpillar? In other words, how wildly is the sampler allowed to move? In other words, can I predict from one step the next? If I can predict from one step the next, the sampler is not very informative, right? Each sample that I'm getting is dependent on the previous sample, which means I might not be exploring the posterior space very effectively, because I'm sort of getting, imagine that you're sort of circling in this lower area of the bowl. You're stuck there, and the model can know, because your steps are very correlated. The values that you're exploring at every different step are very correlated with the values of the previous steps. These is then transformed into something that's called an effective sample size. The more correlated your steps are, the less your iteration counts. Right? Let's say that you had 2,000 iterations after the warm-up. If your steps are very correlated, it might tell you that the effective sample size is 200. If instead your steps are only moderately correlated, you might get a 800 effective sample size. If HMC is so efficient that the steps are anti-correlated, you might get 3,000 effective sample size. That part I don't fully understand, but because the anti-correlation in my head, it's also a correlation, but it never happened to me. But it's something that if you read the guides on effective sample size, that's something that can happen. Why does the effective sample size matter? Well, one is, given the time it's taking to run, we want it to matter. The second is, our goal is to extract posteriors. And so as we draw posteriors, the more samples we have, the more detailed we can be, the more reliable our estimates of, say, the tails compared to the mean can be. As a rule of thumb, if you have 200 effective sample sizes, you can just about trust your mean. Right? If you want to have the tails, well, it depends on how far in the quartile you go, but anything less than 2,000 is useless for 95% percentile, well, the range of the percentiles, right? So this is also something to keep a look at, right? Again, we'll see as we go into multi-level, we'll see these things break. I couldn't make them break on these models. Then we go, before we feed the data, we have priors and prior predictions. So you want to visualize your priors. We've seen that sometimes we transform them, right? So we have a prior on log odds. We want to know what that means for probabilities. So here is a prior on log odds that looks fine. You probably can't see, but it's centered at 0, and it has here -10 and +10. Right? It seems very flat. We really want to cover all the possibilities. But what happens if we convert it to probability? This happens. In probability space, we are expecting the agent to either exclusively play left or exclusively play right. Anything in between is strongly discouraged. Right? Again, it's the probability density that is in the tails of the Gaussian distribution that even if it's very low, everything basically below -3 is roughly 0, right? Anything above 3 in log odd space is roughly 1. There is a lot of probability density outside the -3 to 3 range. So when you squeeze it, then it sort of puts a lot of weight on 0 and 1s. And that's going to skew your model estimates. Does that make sense? Not completely.
What?
Not completely.
Not for now.
Okay. Yeah. So, but in another way, it's what I'm saying is sometimes we do these transformations to make Stan happy. We transform things on a log or log odd scale. Then we need to put priors on that. And we need to visualize what that is doing to our expectations in the original scale once we do the inverse transformation. Another example is that priors combine in complex ways. I mentioned before the reinforcement learning where it's hard to anticipate how learning rate and tau are going to interact unless we simulate. But also in very simple multi-level models, we can have a very simple population level prior, which is a normal distribution, center at 0, and with a standard deviation of 1. So we don't want to go too broad. But then we also have individual variability. And we know that individuals vary a lot. So we might put a normal 0, 2, right, to say individuals can really vary from the population. And so again, when we convert it back to the probability space, we see that the population has a very sensible prior, but our prior for how any given individual is going to behave, since it inherits the uncertainty of the population as well, we actually get that we expect individuals to either only play 0 or only play 1 again. It's not as bad as before, but it's still pretty bad, right? And it's hard to anticipate if we don't put these priors together. So what do we need instead to do those checks? We need, hey, I have 9 minutes still. Okay, well, we need to save all the priors within the model. And we need to generate and save predictions from the prior only model within the model, right? It needs some time to decompress.
Doesn't usually take a while.
Okay, yes. Yeah, but so this is, I don't have plots there and I can run plots here, right? So oh, yes, great. So where would we go and save these things? Right. We've seen it before. Now I'm revealing you all the possible places where you can do stuff instead. There's data, there's transform data. So if you want to do, we've seen before that we might want to change previous choice and feedback into these win and lose variables. Transform data would be the obvious place to do it. We have parameters, which are the unobserved variables. We also have transform parameters, which we haven't had too much an occasion to look at. But for instance, we could put the theta p here, for instance, right? We could transform do the inverse logit on the log odds theta here. But we'll work with that when we'll work with that block a lot when we'll do multi-level models. We have the model, and then we have generated quantities, which is stuff that is not having any effect in the model, but is going to be useful for post-processing of the model. So where would you generate and save the priors and the prior predictions? Yes.
But I feel like you said earlier that it was generated quantity.
Yes. Why?
I'm not sure about that.
Because the distribution of the prior, the specific samples of the distribution of the priors is not something that we use in the model. If you remember, what happens is that simply as the sampler is moving, then it looks these parameter values, how likely is it given the prior, how probable it is given the prior, how likely it is given the data, and then it sums it up. But it never really calculates the full prior. It doesn't need it. It does it only where it needs. So since it's not something that we're going to use in the model fitting, it's only something that we're going to use for visualization and tests. We put it in the generated quantities. Predictions from the priors is the same. It's not something that we're going to use to fit the model. It's something that we can use for visualization and diagnosis. So we put it in the generated quantities. So here I'm adding to something that we had before. So we have in the generated quantities, I say that there's a real theta prior bound between 0 and 1, a real theta posterior bound between 0 and 1. Right? And then we say that the theta prior is the inverse logit of sampling from the normal distribution with a mean of 0 and the standard deviation of 1 or 1.5, right? As I ended up changing it this year. And the theta posterior is the theta p that we were seeing before. It's simply taking the theta in the log odds and transforming it. We can also run predictions, right? We can create a new variable called prior preds, which is an integer. It has a lower boundary at 0 and an upper boundary at n. And I'll get to y in a second. We can also do the same, anticipating the posterior predictive checks, but calling them posterior preds. And then we have that the prior preds are generated using a random number generator, RNG, that follows a binomial distribution with number of trials equal n and using a theta that's equal to theta prior. Where the posterior predictions will have the same random number generator, a binomial, the same number of trials, but instead it should use the theta posterior. Why am I running a binomial with an n equal trial? And I'm doing that for ease of visualization, because visualizing 0 and 1s, one trial at a time, is not going to be super informative. But say, given that the biased agent doesn't change its behavior in the course of the experiment, looking at how many times it picks right is actually a much better summary measure. Right? And I made a note here, so you remember when you check the slides, for other models in which theta changes on a trial-by-trial basis, right, we'll need to generate prediction for each separate trial and or be creative in terms of how we summarize it. So then we plot it. You can see here, I'm taking, well, in the course notes, you'll see that you can extract all the posterior draws and the quantities generated in generated quantities from the model by saying as draws the F, and then parentheses the name of the model. We're going to run a histogram that has the posterior predictions. Am I starting with the why am I starting with the predictions? I don't know. I should have started with the prior. I think that these are the priors, actually. Yeah, these are the priors. I just wrote something wrong there. I need to update it. We then put a red triangle where the actual value is. So if we do 120 times 0.8, and then we can look how many times in our, and remember how many they were, let's say 2,000 posterior samples of theta, we got different values. And we see that we get a pretty broad distribution between 0 and 120, the number of trials in the experiment, and that it's centered around 60, but pretty broad, and the real number is within the range, right? Then what if we instead had a broad prior for theta? So a normal 0,3 instead of 1.5. Then again, we get that familiar U shape. That it really expects that the agent will most likely play all zeros or all ones. This is kind of a sanity check that everything is working as we expect. Then we can do the prior posterior update checks, where we plot as just before, and there you have the code, the prior against the posterior. We see that the prior has, or the posterior has moved its mode compared to the prior, and that its confidence has become much higher, which are both very good signs. There is something called the Gell-Mann test that says that the standard deviation of the posterior should be 15 times smaller than the prior for that to be a reliable learning. I think that any dichotomous choice is crap, so I prefer to look at things and think. And yeah, we're going to skip that. We're just going to do for all our models, right? The Bernoulli model with the beta, the Bernoulli logit on a log-out scale, and the Bernoulli logit when we transform it, right? They're all giving similar information. You don't want to have these because this is hard to interpret. And then we can do the same by overlapping the prior and posterior predictive checks, right? Where we have here the prior predictive checks more faded, in darker blue, the posterior predictive checks, and in red, the triangle that says where the actual value should be. Right? We see that, again, the posterior predictions have gotten much more confident and that they move their mode in the right direction, which is a good start because then next week we'll try to see whether these happens across a wide variety of values. Do you have questions? What are we going to do tomorrow? We're going to start putting in your model. Well, let's see how far your models have come. And then we'll start putting these checks into your models. Good. So thanks for today. And I'll see you in a few hours.